Hi, so good morning. Roger von Peski from Columbia University is going to talk about integrability in discrete random matrix theory.
All right. Thank you, Guillaume, for the introduction. Thank you and all the organizers for putting this program on. It's been a lot of fun. So yeah, as the title says, I'm going to be talking about integrability in discrete random matrix theory. So, you know, I know I'm here at this conference, I'm talking to experts in integrability, but what I want to sort of highlight with this talk is that discrete random matrix theory, so over integers, finite fields, p-adic numbers, I'll mostly focus on the latter, is a nice avenue for application of integrability and a place where there is a lot of integrable structure. And I'm going to talk about two different things which hopefully will illustrate that. First, I'm going to tell you about a probabilistic results about local limits of just sort of the analogs of singular values of these discrete random matrices, which I can state this result without saying anything about integrability, but to actually prove it, I really need it. And I'll say a little bit about why I need it. And then I'll talk a little bit about other symmetry types. What is the analog of the GUE corners process? And there also, there will be a lot of symmetric functions. So let me begin by telling you something which isn't random matrices at all, but rather an interacting particle system. So I'm going to draw this in more of a growth process style. So I'm going to think of this as I have an infinite ordered collection of particles they can be at position 0 or position 1 or position 2, and I'm just spacing them out like this so I don't have them all clumped together. And then they're going to evolve somehow in continuous time. So how are they going to evolve? Each one will have an independent exponential clock. And I'm going to index these particles, so maybe this is the minus first, this is the 0th, first, second, third, etc. And I'm going to fix a parameter between 0 and 1. T is not time, this is just some parameter. And then the rates of these clocks will just be powers of t in geometric progression. Squared. And so you wait, and this picture, I'm not going to draw it, but it sort of extends infinitely far to the left. Okay? And when one of these clocks rings, the particle wants to jump forward. So let's say this one rings. Then it will just jump. So now this particle, which was at 2, is now at 3, or equivalently, I've added a box to this interface. But not every particle can jump forward while keeping the interface, you know, looking like some infinite partition. So if this one were to ring, then it will just donate its jump. So these are 3 particles at position 1, and it will just donate its jump to the lead one, which will jump forwards. So it's like this particle has an effective jump rate, which is the sum of these 3. So there's this move donation here happening. And so just to write some notation, so I'll just call this process S of t and view it as an ordered collection of coordinates. This stochastic process on, you know, infinite tuples of non-negative integers ordered. And so I told you how it evolves. I haven't told you what its fixed time distribution is, but it turns out that there's some sort of stationary data, stationary in a sense, for this object. where if you take its distribution at a given time to have this data, and then you look at a later time, so here t naught is some time, t inverse t naught is some later time. Then these will be equal in distribution. So we can't expect such a thing to actually be stationary because it's growing, right? But we can expect a kind of stationarity in that if we let it grow for a bunch of time and then shift it back, then it should be the same in distribution. And that's what this is saying. So, okay, just take my word for it. There is some stationary data where this thing is true. And so I'm going to call this stochastic process with this sort of shift stationary data the reflecting Poisson C. Okay, any questions so far? Okay. So I claim that this is a universal object in discrete random matrix theory. And now I need to tell you a little bit about discrete random matrix theory. Let me first note a point about this. So if I just cover all of the picture above, let's say height 3, everything down here is evolving in a Markovian way, independent of everything up here. It doesn't matter what clocks over here are ringing. So for the experts, this might remind you of the Markovian projections of Hall-Littlewood processes, and indeed, this is a limit of a Hall-Littlewood process. Okay, random matrices. So I'm going to talk about random matrices in the p-adic integers. I'll ask you to take my word for it that sort of basically everything interesting that happens for random matrices over the integers also happens over the p-adic integers, but is much easier to study there. I'll ask you to accept this. So I'll fix a prime p. And so just recall, I'm going to just recall what the p-adic integers are and how I want to think about them. So usual integers have base p expansions. You know, if I take some integer like this one in base 10, then I can write it as some sum of p-adic digits times powers of p. Here p is 7. And I certainly could write a series like this, which just kept going forever. It wouldn't give an integer, but we just define zp to be these sort of infinite power series in p. Where these coefficients are just base p digits. So they're between 0 and p minus 1. And you can add and multiply these with usual addition and multiplication with carrying. You can also, if you think about it like power series, maybe that's more helpful. So these contain the usual integers. So just as an example, the integer minus 1, which does not obviously live here, and z7 would be 6 plus 6 times 7 plus 6 times 7 squared. Because if I add 1 to this expansion, I'll add it here, I'll get a 7, so then I'll carry a 1, and then add it here, get a 7, carry it, blah, blah, blah. And so all of these coefficients after I've done that will end up being 0. So 1 plus this series is 0, so this series is minus 1. And one reason these are very nice is that they have a very nice canonical probability measure, which the integers don't. So if I just take each of the AI inside this set, p-adic, and uniformly random, then that gives me a probability measure on this. And that probability measure, so it turns out to be the additive Haar measure. If I add another p-adic integer to it, I still get the same measure back. So this is sort of the nice measure, which kind of forms the basis for doing probability here. Any questions so far? So, okay, now random matrices. By the way, what time did we start? I wasn't checking the clock.
Me neither, but
12.
Huh?
11, 12.
Okay, thanks. So you can, of course, take matrices with p-adic entries, and these have analogs of singular values. So if I take an n by n matrix over ZP, then I can always multiply on the left and right by elements of GL and ZP to get a diagonal matrix with powers of P on the diagonal here.
Just a quick question. This AI, they stop at some point?
No, they don't stop at some point. So if they stopped at some point, this would just be the base P expansion of an integer. But you can...
How can this be finite?
Right, so think of a decimal expansion. So, you can just write an infinite repeating decimal expansion, and this is a limit of a Cauchy sequence because everything later is very small. So you can define a norm where high powers of P are very small, and then these infinite expansions are actually limits of Cauchy sequences. Is that helpful? Yeah, okay. Right, so you have an analog of singular value decomposition here, where instead of a unitary or orthogonal group, you have GL and ZP. You can take any matrix, multiply on the left and right. You'll get these singular numbers, lambda 1, lambda 2, through lambda n. And these are a decreasing sequence of integers. So to any matrix, you naturally have a partition associated, and if you have a random matrix, then you have a random partition. Okay. There's another perspective. So you can think of this as an analog of singular values, but there's also another perspective. So, yeah.
Like, why do you get negative numbers here?
Where do you get negative numbers where?
Like for like the exponents, like
Oh.
is it possible to get?
No, it's
Oh, okay.
Yeah, sorry, I said partition, but I didn't write that they're non-negative. Yeah. If the matrix were over QP, you could get negative ones, but I'm not going to talk about that. So these analogs of singular values are actually also the same as the data of a certain group associated to the matrix. Which actually has been the main motivation to study these random matrices. So if I just take ZP to the n, so vectors of ZPs, I can add them. That's an additive group. I can quotient out by the image of this matrix. That's a subgroup. If the matrix is non-singular, this will be a finite, this quotient will be some finite abelian group whose size is a power of p. You can always write these as direct sums of cyclic groups, and the sizes of those cyclic groups are exactly parametrized by these singular numbers. So if your matrix were just diagonal, then you can sort of see that this is true because you're just quotienting each ZP by p to the lambda I ZP. If you have non-trivial U and V, okay, they end up not mattering for this. So the analogs of singular values here also parameterize this random group. And the reason why this has interested people is as n goes to infinity, if I take, let's say, any random matrices with IID entries, which are not too bad, then this random group converges in distribution to a universal random finite abelian group. The name for this distribution, I'll just say the keyword is the Cohen-Lenstra measure. So this universality statement was proven by Melanie Matchett-Wood. And these universality statements are interesting because these random groups also appear in many places that are not obviously random matrix theory. So when people ask about the statistics of class groups of large collections of number fields, or they take random simplicial complexes and look at their homology, or they take random graphs and look at what are called the sandpile groups, they see these distributions that come from random matrix theory. So there's actually not just one distribution. You can take matrices of different symmetry types and get different universal distributions, and they show up in different places. And so there are a lot of random matrix-based heuristics for various of these things. And this is the main reason why people have studied these, but again, not using integrability so much. Okay, that's just a single random matrix. And so it gives you these universal random groups. And it's kind of a non-trivial thing that, that these, as the matrix gets bigger, these groups don't themselves get bigger and bigger. They actually converge to some random finite group. I don't think it's at all obvious that this should be the case. But it is the case, and not just for square matrices, but for symmetric, antisymmetric, rectangular, you always get convergence to a random finite group. And so one thing that is natural is to consider a co-kernel of a product of independent matrices. This is sort of, as far as I see, the easiest way to engineer a co-kernel of a random matrix that will give you bigger and bigger and bigger groups. Because as taking n to infinity won't make them bigger and bigger and bigger, but as you multiply more matrices, then, okay, these co-kernels are going to get bigger and bigger and bigger. So this is, for one thing, sort of the most reasonable model, as far as I can see, of a big or growing random group. And it's also because these co-kernels are the same thing as these analogs of singular values. This is the exact analog of the work on singular values of complex random matrix products. So there's been a lot of work here going back to Bellman, Furstenberg, Keston in the 60s, and people are still working on this. And you see some similar phenomena and some different phenomena when you look at the discrete version. And what I'll describe in this part of the talk is something which is a different phenomenon, because that reflecting Poisson C particle system in the first part of the talk turns out to be a universal limit of these singular numbers. So let me just define a bit of notation. So I'm going to, if I have a matrix A and I have this partition of singular numbers, I'm just going to call that Sn of A for that partition. So again, if it's a random matrix, this is a random partition. Okay, so I want to show you a video of what the singular numbers look like growing as I multiply on random matrices. So I'm told I should share my screen. Okay. So I'm going to draw this partition. This is not usual partition notation, but the first part will be a stack of blocks here. The second part will be a stack of blocks here. And then here I'm going to be multiplying 10 by 10 matrices. So there are only at most 10 parts. Here, most of them are 0. And I'm just going to play a movie where I multiply on these matrices in real time. You can see the number here at this point, it's 7. So let me rewind.
Lambda 1 is equal to 10.
Yes, lambda 1 is 10, lambda 2 is 2, all the other lambdas are 0. Yeah. So let's play. Okay, so lambda 1 is shooting off the screen quite quickly. We now have 7 non-zero parts. And as we keep multiplying matrices, we see this growth process. The blocks keep getting added. And okay, here for 10 by 10 matrices, it will eventually get to 10, and then this wave will sort of not be able to travel any further. But if I were able to simulate 100 by 100 matrices on my laptop, you would just keep seeing this blue wave travel. You note it's going slower and slower and slower as it travels. Its position is about log of the number of matrices. So it goes slower and slower and slower, but it does keep going. And so if you want to understand what are the sort of local limits of these singular value analogs, or what does a big random group like this look like, then you basically want to understand, okay, what are you seeing at the front of the wave here? Okay. Does any questions about this?
Just to make sure, so
yeah.
The first one was only one matrix, and you compute the singular part decomposition of one matrix.
The first partition.
The first
here?
video that the steps of the video. The first
picture was actually a product of 7 matrices. If I'm very fine with the cursor, I can probably get to the point where it's one matrix, but that might take me a minute or two because
And then the reason there is a growth process is because you multiply A1, A2, A3, and so on.
Exactly. So one way to see that this is growth is, okay, you can barely see it here, but you're taking ZP to the n mod A ZP to the n. When you multiply on more and more matrices, this image, A ZP to the n, gets smaller and smaller and smaller. So when you quotient by it, you get a bigger and bigger and bigger group.
You have the chance of getting more larger and larger cap.
Exactly. So this grows, it never shrinks.
Is it still going?
Is it still going? No, it stopped at 350. I guess that's as much as I recorded. Yeah, okay. So, all right. So now I can tell you the theorem. Which is, tell you the assumptions on these matrices, but basically I take the singular numbers of a product of a bunch of matrices. So okay, remark before I say this. The singular numbers of A1, then A2, A1, then A3, A2, A1, you can think of this as a discrete time stochastic process where the number of matrices plays the role of time. This reflecting Poisson C that I gave you at the beginning of the talk is a continuous time stochastic process. So there's going to be some sort of like Poisson type limit of this discrete version to the continuous version. So to state this, I'm just going to kind of put the discrete one in continuous time by taking a continuous time t and then, some scaling factor, and every time this gets past a new integer, I'll get a new matrix. So I'm going to take this growth process on partitions, and then I claim that as n goes to infinity, this converges to this reflecting Poisson C. We're here, what are these matrices? So they're n by n, they're IID. The entries of each one are IID, and they're just from that additive Haar measure, which I said is sort of the nicest measure. And I'm just going to take a constant C that determines how I scale this. Now, let me draw a picture to explain what this limit is. So I have this sort of big blue wave. It can't go as far as n, but then I have some points in the middle, Cn, and I'm sort of scaling time so that I will observe it around this point. And then this here is a finite tuple of decreasing integers. Well, this is an infinite tuple. So I'm going to sort of look at the singular numbers around the Cnth one and then shift Cn to the 0 coordinate here. And I claim that when I do that, and as n goes to infinity, I can sort of look in bigger and bigger neighborhoods around here. And I'm going to see the reflecting Poisson C. So those dynamics that you observed with the boxes getting added in the picture, in the limit, they're described by those simple sort of Poisson particle system with move donation dynamics. Exactly. Okay, is this it? Yep, Jimmy?
Right, so is this like a result then for like a functional result? Like it's jointly true over different t, or?
Yes,
Okay.
very good. It is. It's jointly true over overall, like all the coordinates, SI, or finite collections of coordinates and finite dimensional distributions in T. And you can probably upgrade from finite dimensional distribution if you care to. But yeah, that's an important point. This is a multi-time result. So this is not just saying what you see if you look at that wave at one time. There are explicit formulas for those, but also saying how it evolves. And actually, how it evolves is much simpler to describe than its fixed time distribution, which is some crazy infinite series formulas involving Hall-Littlewood polynomials. Okay. All right. So I haven't said anything about integrability so far, but I promised you that sort of the only way I at least know to get at a local limit result like this is by using integrability. So the key tool here is if I have a partition new, I can look at a certain observable of a random partition, such as the singular numbers of a random matrix. let's say I have the singular numbers of a product of tau matrices. And I'm going to take Hall-Littlewood polynomials. So these are symmetric polynomials and n variables. They have explicit formulas, but they won't really help with this talk. Jimmy also introduced them. Well, he introduced McDonald polynomials, and if you set those to q equals 0, you get Hall-Littlewood. And so observables of random partitions like this, these have been used in other works too. So I know, for instance, Alexei and Michael Wheeler used these for some results with vertex models. And I was sort of trying to prove this result for a while using various things, t-moments, didn't work. Eventually, these were the things that worked. And the reason why these are good is, okay, first of all, they play well with this limit. You can actually sort of see what they converge to. And second of all, you can go back and extract the distribution of your random partition from them. So if you know the value of all of these observables for all partitions with first part at most d, then you can actually get the first d conjugate parts of your random partition. And not just get them, but get explicit formulas for them. So there's an interesting remark here. So as I said, I sort of use these because I tried a bunch of things and they were the first thing that worked. But I realized after doing these computations that they're the same as the main observable, which is used in all these number theory works on random groups. So just call this star. So if I take this Hall-Littlewood parameter t to be 1 over p, then up to some simple factor in lambda, this observable is exactly the number of surjective group homomorphisms from this co-kernel group. So this is when lambda is distributed by the singular numbers of this matrix product into the group which is parametrized into the sum of cyclic groups, which is parametrized by this partition nu. And so basically the only strategy which, as far as I know, exists to prove universality of random groups is to compute these moments for every nu here. So they call these, like, if this group is H, they call this the H moment of this random group. They compute all of these and show that they converge, and then have some general machinery that says that, that suffices for convergence of random groups. So for me, I was just sort of using the first integrable probability tool that worked, and it wound up actually being the same tool that's used in these number theory works. And so furthermore, in doing the computations to extract the distribution, I actually realized that these gave a sort of McDonald polynomial proof of a formula to extract the distribution of a random group from its moments. This was a problem that Melanie Wood, who sort of pioneered this moment method, had mentioned to me, earlier that year. And so I emailed her and was like, oh, hey, I can do this with Macdonald polynomials. At that point, she had already figured out how to do it without Macdonald polynomials. So this was in some work of her and Will Solin. But I just want to highlight that sort of doing things with Macdonald polynomials gave an alternate proof of, I think, a fairly non-trivial fact about these group moments. So there's interesting interplay between the tools that we use and the main tools that are used in these number theory works. And I just wanted to highlight that.
But what is the result that you're talking
The results is an explicit formula which tells you if you know the values of all of these moments for a given random group, the value of these as new ranges, then it's an explicit formula for the probability that your random group is isomorphic to any given group. Okay, so it's the analog of like the moment problem. Like given a set of moments, can you write down the probability distribution with those moments? And is this unique? Blah blah blah. Yeah, does that make sense?
Yeah. Just one last thing
Yeah.
about the equation star.
Yes.
Does t appear in the function itself, the expectation? Capital T.
Capital T.
Yeah.
This.
Yeah.
Well, I mean, okay, capital T.
So
Capital, yeah. So of course the measure depends on capital T, but no, the function does not.
That's
Yeah. So this ends up being a Hall-Littlewood measure with a principal specialization, and that makes this, by the Cauchy identity, end up being a single Hall-Littlewood function. You can write integral formulas for that by the Macdonald inner product, and these integral formulas are sort of the right thing to take your limit.
This hadn't worked. They derived integral formulas in some other.
No, so they don't have integral formulas. They just prove convergence of these observables using sort of additive combinatorics type techniques. And then they have a general machine which says that you can extract the distribution of a random group from this. Now, what they do is a bit different from what I was doing here in that they're looking at cases where this group converges to a random finite group rather than growing without bound. So I couldn't use their machinery here, but it's using the same observables, and it's of a very similar flavor. Yeah. Any other questions? So talk about local limits and integrability. So okay, you said I started at 1112. So then I should stop around 102. Is that correct? Contradict me now while you can.
You have a 2-hour talk?
Sorry, 1202. Yeah, the other one, 1202. Yes? Okay. So in the remaining bit of time, so this was sort of an asymptotic result that to state you didn't need any integrability. And now I just want to show you some sort of nice exact results, which we haven't used for asymptotics yet, but give a bit of the flavor of, I don't know, of the nice formulas that are true here, some of which lie behind this. So in classical random matrix theory, we have the GUE corners process. So you take a Gaussian Hermitian matrix, you look at its eigenvalues and their joint distribution with all of the eigenvalues of its corners. This ends up being something sort of very nice and simple. And it's natural to ask, what is the non-Archimedean analog of this corners process and other similar ones? And they end up being very nice, so I want to sort of illustrate that. So let me take a Hermitian matrix. N by N. So I'm going to take VP and then just adjoin a square root of -1. To have the square root not already in ZP, let me just assume that P is 3 mod 4. You can do something else when it's not. So I can define complex conjugate, just in the usual way. Conjugate of root -1 is negative root -1. And then I'll just look at a random matrix where its conjugate is its transpose. And other than that restriction, the entries are IID Har. Now, another thing that I could do, so there are various corners process also, like the antisymmetric GUE corners process in usual random matrix theory. So I could also take a 2n by 2n matrix which is antisymmetric. And again, subject to this restriction, all the entries are IID Har. Another color. Finally, this is in some sense the simplest case. I could take an n by n matrix with no restrictions. All the entries are just IID Har. And I can ask if I know the singular numbers of one of these, what is the distribution of the singular numbers of their corners? So I'll start with this case. So if I know the singular numbers, the singular numbers of this matrix B, these will be some partition lambda. And it turns out that the probability that you get a given one is a Hall-Littlewood measure. And then you can ask, what is the probability if I remove the first column? So I'll call that matrix B n by n minus 1. It's an n by n minus 1 matrix. What is the probability, the conditional probability that I get singular numbers mu? And that conditional probability will be sort of the Markov transitions of a Hall-Littlewood process. And you could then say, okay, let's now remove a row and ask how they transition. So in other words, if you know mu, what are the singular numbers of the next partition? So we now have an n minus 1 by n minus 1 matrix. And the transition probabilities here are also these Hall-Littlewood ones. So this is for the case of a matrix with no symmetry. And here this parameter t, use that to be 1 over the prime p. Okay. Now the interesting thing is it turns out that almost exactly the same thing is true for the other cases. So for the alternating case, this is a 2n by 2n matrix, but it turns out that the singular numbers occur in pairs. So I'm just going to only pick one from each pair, so I have a partition of length n. And so if I look at the probability that that is lambda, it will be this exact same formula, but with t equals 1 over p squared. And then if I look at the top left, n minus 1 by n minus 1 corner, which I'll write as a 2n minus 1, the probability that I get mu is given by this exact formula, but with t equals 1 over p squared. And you can maybe see where this is going, because if I now again take a corner and have 2n minus 2, the conditional probability is this exact formula with t equals 1 over p squared. Now in the Hermitian case, so things look good so far. If I take the probability that my singular numbers of Hn are a given lambda, this will be given by this formula. Now with t negative. And if I go down here, it turns out that if I want to look at the probability that its top left n minus 1 by n minus 1 corner has singular numbers nu, that will be given by the composition of these two Markov maps when t is minus 1 over p. And you also have to put a minus sign there, but okay. So it's basically the same story, except that you don't actually have this intermediate step. But it's actually a bit funny and a bit different because these Markov maps are not Markov maps anymore when t is minus 1 over p. So these probabilities can be positive or negative depending on the sizes of the partition. And this one also can be positive or negative. And actually their product for a fixed mu can still be positive or negative. But when you sum over all of these sort of fictitious partitions mu, then you will actually get a non-negative probability that you go from here to here. And it is sort of the probability of the corners process. So I thought this was very interesting when we saw it. And by the way, I should say, these two recent work with Jiahe Shen. And this one is a bit older. So somehow these formal McDonald processes where you have formal transition probabilities, they've been used in proofs in the literature a fair amount. But I at least had never seen one sort of show up in nature. And here it is. You ask, what is the non-Archimedean analog of the GUE corners process? And here it is. It shows up. So that's all that I wanted to talk about. But just to conclude, there are a lot of interesting questions, interesting analogs of results in classical random matrix theory here in the discrete world. Some things are similar, some things are different. There is a lot of integrability. I'll stop there. Thank you.
Is there any sense in which you can recover results from classical random matrix theory?
I don't think so. Yeah, so you mean recover from these results about p-adic random matrix theory?
Is there a limit from p-adic numbers to just real and complex numbers?
I don't think so.
I think, okay.
All right, what were you about to say?
No, just, there is some sense in which the GUE is some special case of a log gas.
Yeah, so you can certainly get classical random matrix theory as limits of McDonald processes. Like you can sort of take this Heckman optimum limit, but somehow the Hall-Littlewood limit and the Heckman optimum limit, like you can't get either one from the other. So yeah, once you've taken one, you kind of can't go to the other. But you do like formulas like this, at least for the orange case. If you replace these by McDonald polynomials and then took the Heckman optimum limit, you would exactly get the formulas for like the singular values of corners of a matrix with p-adic complex Gaussian entries. So there are like extremely close structural parallels between the two settings, but I don't know of a degeneration from one to the other. Yeah.
If you take Tito.
Yeah, good question. So if you take t to 1, so okay, I don't think this corresponds to classical random matrix theory, but it is an interesting limit. So like that reflecting Poisson C, if you take t to 1, then sort of all of the particles have the same jump rates in the limit. And you actually, it sort of gets wilder in that limit, and you have to rescale things. And when you do this, your height function there after you've done this rescaling becomes some kind of thing in the Edwards-Wilkinson universality class, although it's not exactly it's not exactly the additive stochastic heat equation, but it's some other stochastic PDE. Or sorry, just SDE. So yeah, it is a probabilistically interesting limit, but as far as I understand, it sort of leaves the world of random matrix theory. Jimmy?
So, like, do you know it's like anola duality that shows up when you look at like the unitary group over finite field? Like, is this like minus 1 over p kind of related to
it should absolutely be related to that. And I sort of looked at those papers and tried to understand something, and I don't have anything I can tell you, but it should 100% be related. Yeah.
Roger, again?